simple harmonic oscillator. So last time we did that already. We have the Hamiltonian p squared over 2m plus kx squared over 2, right? And we can rewrite it as p squared over 2m plus omega 2m over 2 if omega is square root k over m, right? Just take it, we did that. Now, and then what do? We decide to quantize it. So we're going to convert p and x to the operator. And that's why we use Hamiltonian, because this is the linkage between the classical and the quantum mechanics. The velocity is not clear to me, or actually in quantum mechanics, it does not, is the relationship between the position and the velocity does not have the relationship of position and the momentum as what it has, right? So what do we mean when we promote the p and x to the operator, right? It becomes a matrix, right? And the eigenstates of the momentum will give, apply this operator to p, I will get the momentum, right? I apply the x, which is the location operator, into the state x, which is the eigenstate of x hat, I will get a position. So last time, for example, I say that, wow, I may have unlimited, this is an infinite space, right? So my particle can be at any point. Maybe it is at location 5. Then how do I label it? It is 0, 0, 0, 0, 1, the fifth location, 0, 0, 0, 0, right? You can think of this. It's continuous, but now I make it discretized, but it's infinite, right? So this is maybe x, right? This may be equals to x, or x equal to 5, right? It's just a way to write it. Now, here again, if you go through J.J. Sakura's book, right, it will show you how it came up with this uncertainty, this anti-commutation relationship in the chapter 1. It's a very rewarding to read it, but it's pretty lengthy. But anyway, you trust it. X and P, they do not commute. Means XP minus PX, right? This is the symbol we learn when we deal with the polyspin matrix, right? We learn about anti-commutation and commutation relationship for the polyspin matrix. XP minus PX equal to IH bar, right? Just take it for granted, okay? Now with this then, nothing special. I just replace the P equals P hat and then X equal to X hat. And this is a matrix already. I can, if I want to rewrite a matrix form, this is the quantum treatment of the SHO already. Okay, we have not done anything yet. This is just the background. Is that okay? So this is the Hamiltonian in quantum mechanical description for SHO. Okay. Now, then, how to see its effect? I'm going to introduce two operators. One is annihilation operator, another is creation operator. And this is defined this way. Right? How we define this? I think this is just because this gives a nice treatment of the math that will give what we want. Later you will find that annihilation really kills one of the photon, one of the oscillation. In the EM case, it kills one of the photon. Creation, it creates one photon or one new photon. What is photon? It's the vibration, right, of particle, photon, right? So by doing this, you just take, don't be too worried first. Just agree, right? I have the rights to define anything, right? Now just trust me, I want to define in this way. A equals to this x hat plus IP hat divided by m omega times this constant. A dagger equal to this. Right? And you do see A and A dagger, they are what? They're the adjoint of each other, right? Because if I put dagger to A, I will go to put negative to I, because X and P, they are Hermitian, right? X real, P is real. So nothing special, right? So this is, they turn out to be the adjoint matrix of the other. Okay, but they are not Hermitian by itself. So do you expect you can do a measurement? Is that observable? No, right? Because it's not Hermitian. It's not going to have a real eigenvalue. But it has some very important implication. Now, first of all, this one is just for math. I want you to go through this. In this, after the class, last time someone came to me, why this two does not cancel? Well, because they don't commute. Very good. Because xp is not equal to px, right? So this is math, practice it. For those physics people, maybe you know this very well. But anyway, a dagger commutation equal to a dagger minus a dagger a. The rest is just substitution. And you just need to be careful when you do multiplication, because since elementary school, we just don't care about a times b and b times a. We treat them the same. But now you need to be careful. Do the distribution rule. X distribute to x, xp, p, px, p, pp. Okay? Do not say this is xp, right? This is px. Just do it. You can do it. Even you bring this to a first grader, right? I think they can do it as long as you tell them, do not think that a times b equal to b times a. Then they will get what? Right? Just follow the rule. And I think that this is something we always make the mistake as in the process, right? As long as you don't make this mistake, you can spend more time to understand something deeper. Now, anyway, I introduced it to operator. Annihilation operator, creation operator, and they don't commute, it is equal to 1. Okay? Any questions? Now, if no, is messy. Then I try to introduce something called number operator, right? Now it's just, you just look at me how I do it. And then you will certainly understand what's going on. So we define a number operator, n. Now, so I'm a little bit lousy. Usually when we talk about operator, we'll add a hat on top of it, right? So you need to be ready. Sometimes I forgot to add it. You need to know that it is an operator based on the context. This is the number operator, right? So basically here, I also should put hat to here, right? This should all have the hat, but I was just lazy, right? Because it's an operator, right? But I assume that you are okay with that. A hat times A is a number operator. What does it mean? Why I call it number operator? So let's again practice the math. I know it is maybe boring for some of you, but I want to go through this because you may get stuck by just doing this math as you're not familiar with this. I'm going to do A dagger times A. And actually, I should not have to redo it because here I already have A dagger times A. This is the whole term that I have. Do you see that? Start with m omega 2 h bar, and then this, right? So I will copy it, but I just tell you that if you had the last page, you will be able to see this already, right? So this is equals to m omega plus I xp m omega plus p squared divided by m squared omega squared. I just copy this again. If you cannot copy, that's fine because you already have this here, right? You just say refer to the last page. But the most important thing what I get here is this give me m omega 2 h bar times I x hat p hat divided by m omega minus I x hat. No. P hat x hat divided by m omega, right? So what am I doing? This should be, I think I did something. This should be, I'm sorry. I just, I really should not do that. Sorry, I need to redo this. I did not copy it right. I keep thinking that I can erase that, cancel that. So let me do it one by one. Let me start with p squared, right? P squared on the last term. what do I get if I do p squared? It becomes p squared divided by 2h bar m omega. Is that okay? Right? This one times this one, 2h bar, right? And then I do the x squared. X squared, of course, is m omega x squared divided by 2h bar. Okay? Now, and then this m omega 2h bar times this thing, you find out that it's just like what you do here. M omega 2h bar times this thing, right? But it is just maybe 2 times, right? This is just equals to I divided by m omega divided by 2h bar x p, right? So what am I doing here, right? I just do this again. This is m omega divided by 2h bar. So I have this here. And then I have this difference, right? Look at this difference. This is the difference I'm talking about here, right? Minus px plus px, xp, minus px plus xp, right? Minus p plus xp. So these two add together, right, should give me the something like this if you try to go through the math, right? Because this is, what is this? xp minus px. I may actually confuse you. This is xp minus px. So I do have a xp minus px. Is that okay? So this one gives me xp minus px. And then I take out I m omega, right? And then I still have m omega divided by 2h bar. So I confuse you by referring to the last page. But what is xp? Do you remember? XP commutator? IH bar, thank you. Right? So as a result, the whole thing becomes, before I do that, maybe let's recognize this first. What is this term? What is the Hamiltonian? Do you remember? P squared divided by 2m, omega m divided by 2x squared, p squared divided by 2m, omega m x squared divided by 2. This is equals to 1 over h bar omega h. Or you think about this here, right? H is this one, right? If I divide this by 1 over h bar omega, p squared divided by 2m h bar omega, p squared divided by 2m h bar omega, omega square m divided by 2, omega square m divided by 2 h bar. So this is 1 over h bar omega, right? And then you just told me that this one, I forgot this, equals to IH bar, right? This 2 is going to get cancelled. M omega and M omega get cancelled. And you times IH bar, then it becomes negative IH bar 1 over 2. Is this okay? Right, so let me remind you. H equal to 1 over 2m, p squared divided by 2m plus m omega square x square divided by 2. Right, so you compare these two. The only difference is that this one have a h bar omega in extra because this is omega square, so h bar square, h bar omega, right? And this term, this got cancelled, and this is equals to I h bar. So I times I, h bar got cancelled, negative 1 over 2. Okay? And we say this is equals to the number operator, right? So as a result, what is the Hamiltonian? It's equals to h bar omega times n plus 1 over 2. Right? So you see the number operator has some relationship to the Hamiltonian. It is the n plus half times the h bar omega. What is omega? Do you remember? And this is what? The resonance frequency of your simple harmonic oscillator. Yeah, it's a characteristic frequency of your system. And basically, from here you see that the total energy is due to h bar omega, which is the energy quantum times some integer plus half. Right? So naturally you think that, oh, actually the system looks like is how many energy quanta you have times the h bar omega. Right? But what is the real meaning of n? We need to continue. But this is a very important equation. Now I ask you, why do we get 1/2? We get 1/2 because of xp. If there's no xp commutation issue, this won't be there. This is going to be 0. Right? So this 1/2 is basically saying that even I don't have any particle there, in the vacuum, I also have some vacuum energy. Right? I go too far, but in this page, just understand what is the how this number operator is related to the Hamiltonian in this simple harmonic oscillator. Okay? Any questions? So let's continue to understand the meaning of the number operator. Why we call it number operator? Now, since we already call it number operator, then we assume we can do this. For this operator, it must have some eigenstate. And we call it n. Right? So basically, we are assuming the eigenvector of the number operator be n. And then the eigenvalue of the number operator be n. Right? For any operator, I must have an eigenvector, right? It just, I call it n. It turns out n has some physical meaning, but I call it n. Is that okay? So if this is the case, I apply the Hamiltonian to the eigenvector of the operator. What does it mean? You try to say, what is the energy of this state when you have n particle? And since I know that this is h bar omega times n plus half, and it is linear, so I can further make it h bar omega n operate on n plus half n, right? What is n operates on n? What is this n operator operates on its eigenstate? Huh? Eigenvalue times the eigenstate, right? This is given. So this is just equal to h bar omega n times n plus 1 over 2n. I can factorize out h bar omega n plus half operates on the eigenstate. So basically, you see that n is also the eigenvector of the Hamiltonian in the simple harmonic oscillator case. Yeah, so I introduced something called n. There was a reason, because it really represents some particle number. And the total energy of the system turned out to be with eigenenergy. You can call it eigenenergy because the eigenvalue of the h, of course, is called eigenenergy, right? or you just call it eigenvalue of H equals to what is based on this equation. H applied to n equal to this times n. What is the eigenvalue of this system? H bar, the whole thing is the eigenvalue, right? So it has an eigenvalue which is En equals to H bar omega n plus 1 over 2. So now it becomes clearer what we are doing. So somehow if we come up with an operator called n, and this n is A dagger times A, it has an eigenvector. Everything has eigenvector. But turn out this eigenvector is also an eigenvector of the H, of the total energy. And turn out the eigenvalue is a quantum of energy, H bar omega. Omega is the resonance frequency times n plus 1. So I can even think of this as the eigenstate is talking about how many quanta I have. I just think about this simple harmonics oscillator. I have 1 quanta of energy, 0 quanta of energy, 3 quanta of energy. Then it has this amount of energy. Any questions? Maybe it's still not clear, right? But let's continue. Let's just go through all of them, and you will see something very interesting eventually. But let me see, what do I want to do? Let's just again practice some math, okay? This is just to prepare for the future homework. What is the commutation between n and a hat and a? Say again? Na minus an. That's what I said, right? This just, you have not seen this before, so it's a good exercise. But what is n? Can you tell me again? A dagger A, very good. So what I'm trying to evaluate is actually this one. Is this 0? No. Or at least you should say, I don't see that yet. Because you cannot say, I can swap A and A dagger. A and A dagger do not commute, right? A dagger A commutator equal to what? A dagger A equals to, oh no, should be A dagger, sorry. A dagger minus A dagger A equals to 1, right? So this is a skill. So there are many equations you can memorize if you're really doing quantum mechanics, but we don't need to do that in this class. We just do it from this basic, right? So this tells me that A dagger A equals to 1. No, what should we do? Equals to what? A dagger minus 1, right? I just put A dagger A to the right and then move 1 to here. So A dagger A equal to this, right? So my goal is to do a substitution, right? I have A dagger A at the front, right? I put A dagger minus 1. This is A dagger A times A. Do you see what I'm doing? I substitute A dagger A by A dagger minus 1, right? Minus A dagger A dagger A. I mean A dagger A. This one give me A dagger A, right? Got cancelled. So eventually I get negative A. Okay, so their commutation give me A dagger, still the operator, but negative of this annihilation operator. So to save time, I asked maybe let's do this in the homework, right? You can just ask ChatGPT, I'm sure it could give you the result easily. What is this? This turned out to be A dagger, right? Do homework. And again, you use the skew I just told you, you will get this, right? Your goal is to come up with something you can cancel, right? This is just a practicing the skew. Nothing special, no physical insight yet. Is that okay? Okay. Now, then why do we want to do this? We have this basic equation. Now, I want to ask you, if I put the n operator in front of a dagger n, what does it mean? You can even think of this as, okay, I first put the a dagger to n. I have a state which is n, right? After I put the a dagger to n, what do you get? You get another state, right? But you don't know what state is that. However, I will try to measure. I put the n operator to it, try to measure how much n it is now. Do you see what we are doing here? This is just separated to show you that n a dagger n is just like I first apply a dagger to a vector. So it becomes another vector, right? Because all the operators are just matrix, right? You rotate the matrix into hyperspace. Now I becomes a vector. So now I apply n to it to see what I get. Okay, let's see what I get. Based on what we got earlier, n a, maybe I just use this directly from here. I'm doing a dagger though. So this one I need to rewrite it, right? This one I just need to write this as a dagger minus n, not a, I mean, n a dagger minus a dagger n, right? I'm just spelling out this commutator, right? So what is n a dagger? Based on this equation, can you tell me what is n a dagger? Very good. It's equal to a dagger plus a dagger n. Right? I did not do the factorization yet. Is this okay? N a dagger, I'm using this equation. N a dagger equal to a dagger times a plus, right? And what is this? As you said, it is a dagger plus 1. When we say 1, by the way, what is 1? 1 should be a matrix, right? It means identity matrix here, right? Because this a dagger is a matrix. Okay? But I just put it 1. Then I have this. Now, what is n operates on n? Sorry, I think I did something wrong. What should be this? This is not a dagger plus 1. It should be what? A dagger times 1 plus n. Right? So, but maybe it's time to make this a vector plus identity times n. So what is 1 plus n applied to n? What is identity applied to n? N, which is 1 times n. What is n time applied to n? Lowercase n. Do you see this? Because identity times n is equal to 1 times n times n is equal to lowercase n times n, because that is the eigenvector of n, right? Now this is a number or a matrix. It's a number, because this is the eigenvalue, right? If it's a number, I can move it around. I actually also want to swap the order, call it n plus 1, a dagger n. Is it okay? So what have I found? Look at this. I apply n to this state, and then I get n plus 1 to this state. Okay? Then what does it mean? It means A dagger n must be proportional to n plus 1 state. Right? I give a number, let me just call it equal to a coefficient times n plus 1. Right? Because it's just like saying that this is a vector, right? Because I apply an operator to the eigenstate n. And then I try to measure it. It gives me back the original vector, which is A dagger n, but with an eigenvalue, which is n plus 1. Then it means this vector must be equal to n plus 1, except that with some proportional constant. Let's think about this. Any questions of what I'm doing here? Yeah. This last line? Yeah. Again, how about I do this? If I call this n dash, I call this n dash. If I call this n dash, isn't that I'm getting n dagger applied to n dash equal to n plus 1 n dash? What do we say about number operator? If you apply to n, I get n coefficient as n, right? Now apply to this vector, I get n plus 1. Then n dash must be what? If I apply to this guy, I get n plus 1. I'm supposed to get n dash n, right? So n dash equal to what? Apply to n dash, I should get n dash, because this is the eigenvector. I will get this eigenvalue. But this proves that it is n plus 1 n dash. So what is n dash? Can you speak louder? N dash equal to n plus 1. Exactly. Right? So what I'm showing here is that A dagger a new vector, which is n dash, equals to A dagger A, which is related to n dash, which is n dash, I should say. Right? Must be n plus 1, this new vector. Okay, but it doesn't mean that it's exactly n plus 1, because here I still have a constant that I can manipulate. Because even this is 1,000 times n plus 1, this I also have 1,000 times n plus 1, they get cancelled, right? Is this clear now? Basically what I'm saying that I apply the A dagger to a vector, and then I measure it, I get to n, I get n plus 1. Then that it means I promote it from n to n plus 1 state. Question? Yeah, I use this equation because n commutator with A dagger equal to n A dagger minus A dagger n, right? This one, right? But I did not prove it. You prove like this one, you will get this equals to A dagger. So then n A dagger, this whole thing, equals to A dagger plus A dagger n. This equals to this. Yeah. And then I plug in. Okay? Good. So again, similarly, right, for homework, I can show that n dagger A to n, you can guess, what is this? What do you think? So by the way, we just call creation operator. You know, I create one extra quantum of energy by applying A dagger to it. It becomes n plus 1 instead of n. Now I put the annihilation operator to it. What do you think? What we will get? Say again? Yes, negative. But I start with n, right? So what do you get? N minus 1, right? Because this is N becomes N plus 1, right? And now you have annihilation operator. You expect to get something like this. Okay? So again, we expect, let me call this D1 maybe. Okay? So I will expect to get this again. Tell me that A operate on N equals to D2 N minus 1, right? So basically, it's just telling me that this A dagger and the A, they are the creation operator. I have N particles, N quanta of energy. After I apply this creation operator, I becomes N plus 1. Because remember, what is this state? This is telling me how many quanta of energy I have. It's the eigenstate of this number operator. When I apply number operator to it, I will get N, how much it has. Now, if I apply this to here, I becomes N plus 1. Apply this to here, I becomes N minus 1. Okay? You do need to memorize this. You see, easy. Because actually, when you go to this second quantization, all this thing becomes very easy at this level. It's just describing I add one more particle, remove one more particle. You can think about this mathematical treatment is so elegant. Think about that. There's a rigorous quantum treatment, and what you are saying is just that, see, I add this operator, have one more particle. How can you describe this mathematically in all the things you have learned so far in EE, right? Okay. Now, then I will need to continue to do normalization, because just now I did not tell you how it is normalization. I just told you that A dagger N equals to D1 N plus 1. Okay? But any vector needs to be normalized, right? Because you remember the vector in the Hilbert space, right? Or in quantum computing, in quantum mechanics, you need to have the unit length of 1, right? So how do I find the length of the vector again? The square of the length. Use what? Dot product, inner product, right? So let's do it step by step. If this is called V, what do I call it? I call it N dash, right? N dash. Right? I can call this N dash. Let's think about that. Is this the one I need to do? Correct? No. Right? That's the normalization, right? What is the bra version of N dash? How do we write it? Well, I need to write the bra version of N, right? But how about for A dagger? How do you write it? It becomes just a joint matrix, right? Become A. Remember this? Right? So the whole thing times itself, which is A dagger N. Yeah? And this one needs to be 1 in order to normalize. Okay? The length needs to be 1. But what is A dagger? This is a little bit difficult to see. I mean, I need to find what is A dagger. It is equals to, you don't know, I mean, it's difficult. You will use the commutation again, right? There are many ways, but I'm doing a dumb way. Where's this? A dagger minus A dagger A equal to 1. So A dagger equal to 1 plus A dagger A. Are you okay with this? A dagger equal to 1 plus A dagger A. You may say, what is the point of doing that? That is because I recognize this is what? A dagger A. It's the number operator, right? You can recognize because you just learned, but I know that because I have a cheat sheet, right? That's it, right? So you use this, then this becomes, you are applying 1 plus n, right? They are all operator on n. But when you apply 1 plus n to n, what do you get? You apply first 1 to n, what do you get? N. 1 times n. And then you apply n to n, what do you get? N times n, right? So this becomes n, 1 plus n. Now, times n. And now this is a number. I can take it out, right? So this becomes 1 plus n. Or did I do something wrong? Yeah, I thought this needs to be 1. I think I keep doing something weird. Sorry. Just follow my cheat sheet. So so I need to incorporate the D1, right? So let's go back again. Sorry. N dash n equals to this times A times this 1, and it needs to be 1. And then A dagger equal to 1 plus A dagger A. What did I do wrong here then? Yeah, yeah. I say something very wrong. This, sorry for that. This one doesn't have to be normalized. That is the whole problem that I am doing. A dagger n doesn't mean that it is normalized. I rotate, go to another vector, right? N plus 1 needs to be normalized, but A dagger n doesn't need to be normalized. Because A is just an operation, maybe I'm doing some stretching. So bad, I'm sorry. So it doesn't have to be normalized. Okay? However, this one also equals to n plus 1 d1 star times d1 n plus 1. Right, so I come back to here. Is this okay? So I'm trying to equate this equation, right? So I make a big mistake. Hopefully you learn from mistake. N dagger n doesn't need to be normalized, right? What need to be normalized are the basis vector 1, 2, 3, n plus 1. N and n plus 1 needs to be normalized. Not A dagger n need to be normalized. Is this okay? Is this clear? Which one say again? Both needs to be, no, nothing is normalized. N and n plus 1 need to be normalized, but not A dagger n or dn1 times n plus 1. N and n plus 1 need to be normalized because they are the basis vector. But n dagger times n doesn't need to be normalized. I just operate, maybe I stretch it or I do something, right? Because this is not yeah, okay? So in order to find out their magnitude, then I do the inner product of the left part. This is the inner product of the left part I just showed you. How about the right part? We do the same thing, but this is not operator. We take the complex conjugate. Is this okay? Right? Then I will continue what I'm doing here, right? On the left part, I just call it left hand side. Then what do I get? This is what we get. Just what I discussed. Then this one becomes 1 plus n times n. But what is n inner product n? 1, right? Because they are normalized. N inner product needs to be normalized. So the left-hand side is equal to 1 plus n. Okay? How about the right-hand side? D times D is what? Just the magnitude of D, right? So it is just equal to the D squared times n plus 1 inner product of n plus 1. So this is equal to D squared. So what does it mean? D has the magnitude square equal to n plus 1. So D equals to square root n plus 1. Okay? So based on this, what does the raising operator does? It operates on n. It becomes square root n plus 1 times n plus 1. Right? Why? Because earlier I showed you that A dagger operate on n becomes D1 times n plus 1, right? And now I found out that the D, this is D1. I found out that D1 equals to n plus 1. And that's why I have A dagger n equal to square root n plus 1 times n plus 1. Yeah?
Are the creation and annihilator operators unitary?
No, they are not. You see, they don't preserve the length. Yeah? Good point. Yeah, he said no. Is it okay? Okay, so where? Which one? Left-hand side, yeah? Okay, so this one becomes this one. Is this okay? And then now it becomes 1 plus n, right? You take out 1 plus n, and then n inner product n is 1, right?
So you're just saying that a dagger
No, and then on the left-hand side, it is equal to d1 square. Yeah. I hope I hope the fact I keep making mistake only make you better. You won't repeat my problem. You see that I make a big mistake. Again, my concept is not good enough, right? Because I should not keep thinking that A dagger n equal to 1, because it's not unitary, right? Like what you said, right? So that's why we need to normalize in this way. Okay. Now, therefore, how about do it yourself again? I'm slow. Maybe in the homework. What is A operates on n? What do you want to guess? What is that? N minus 1, that is correct. But instead n plus 1, it is square root of n. Okay? Just do the normalization, you will get it. Okay? Follow the same approach that I have done. Okay? So here, clearly show you that we also get the normalization constant, and we also know what the annihilation and creation operator does. Right? So we learned the math skill, some critical concept, you see I mess up, but most importantly is that we also done the, we understand that annihilation just add one more quantity, one more quanta to the system. right? I mean creation, add one more quantum. A dagger n becomes n plus 1. A n becomes n minus 1. It looks like I'm taking 1 unit of energy from the system and put 1 energy into the system, respectively. Yeah.
Why is that useful?
I say you will see that later, okay? But now but I feel that you should appreciate I'm using a mathematical tool to describe how I add a particle to a system. Think about how you can have a mathematical tool to do that. How to describe adding a photon to a system? Have you ever think about how to do that? You cannot, right? You solve Maxwell equation, you are not adding photon, no matter how complicated it is. My system now have a variable number of particles. And that is the great thing about second quantization. Okay? Yeah, think about how is that useful? Of course, later you will see that. Very elegant, right? Okay, how about the value of n? What value can n take? Right? So here I'm going to show you that it can only be positive. And it only be integer. Can it be 0.5? No, right? So let's see why, okay? So we know that n dagger n, I better follow cheat sheet this time, equals to this. A dagger n, this one equal to this, right? Now, what if I do one more time? I do a square n. What do I get? Well, it means that I first do an a on n and then do the a one more time, right? So when I do it the first time, what do I get? Square root n minus 1. Correct? Now I do one more time, what do I get? Square root n minus 1, n minus 2. Right? I lower it from 10 photon to 9 photon, apply one more time to 8 photon. And I keep accumulating this constant, right? Because square root 10, square root 9, square root 8. If I keep applying this many times, right? Will it be negative? Okay. No, I mean, just this formalism. Let's see if we can be negative. Yeah, it doesn't make sense if it becomes negative. What is the meaning of negative photon in the system, right? But let's see why we can prove it. We know that n, I should say this. If I try to find the average number of photon of this state, that is how I find it. Do you remember? Right? Because n is the operator. You sandwich the state on the operator. But this is very clear, right? This equals to what? This equals to a dagger a. Right? So I'm doing something that like this, right? Because n hat equal to a dagger a, right? So this is basically equals to the inner product of this one, right? The inner product of an is just equal to this one, because I need to take the bra of n and take the Hermitian, take the adjoint of a dagger, right? Correct? This inner. But for inner product, what does it mean? The inner product of any vector must be larger than or equal to 0. It must be positive. But at the same time, what is this? This is equal to n. Very confusing. Because this is operate on n, then you get small n, right? This is the eigenvalue. So this is equal to n, which is n, right? Because this is just saying that I have a state that have n photon. What is the FH number of the photon in this state? N. That is exactly what it is saying here. So that's why I get n, right? So here I prove that this FH process is just the inner product of an arbitrary vector, of n vector, which must be larger than 0. So it tells us that n must be larger or equal to 0. Okay, so you cannot have negative n, right? However, on the other hand, if I keep doing this lowering operator, isn't that it may hit 0.5 and then becomes negative 0.5? I can do that, right? Then it will violate this process. So I need to be integer so that you start from integer 10, 9, all the way to 0. Once you don't have photon, you have nothing. When you apply this annihilation operator, it gives you 0. It won't continue to reduce. So that's why it needs to be zero, 1, 2, 3. It must be it must be the natural number 0, 1, 2, 3 for n. Okay? N must be this, right? So what is the ground state? What is the lower energy of this system? It is when n equal to 0. With the energy equal to what? H bar omega 0 plus half equal to H bar omega divided by 2. It means even you don't have the photon, you still have some energy there. This is called the vacuum energy. And this is important actually for the noise, because this energy is going to create electric field, even you don't have any particle there. Right? The vacuum, this is a fluctuation, and you suddenly create some electric field to decoherence your qubit, which you cannot avoid them, even you are in an empty space. Okay? And why we have this half again? Remember how we get this half? Commutator. Very good. And why we have the commutator? Quantum mechanics. Right? And why commutator is related to uncertainty principle. And then that's the reason. You actually is uncertain in terms, for example, energy and time. So for a short time, you actually don't know exactly what the energy is. So you cannot say it's absolute 0. It's just like you can borrow some energy from the God for 1 picosecond and then return it back. You still conserve the energy. However, you cannot detect it. It's like all those corruption in the bank, right? Just embezzlement, took away $1 million to do investment. If you're fast enough, you can return it back. No one will discover. Something like that. Okay? I still want to go more, right? So then I want to talk about the energy eigens, more about the energy eigenstates. Now, what did I say? So let's look at this. A dagger 0, what will you get based on what you have learned so far? At least you need to know that it becomes 1, yes.
And then
Square root what?
square root of 0.
0 plus 1, always larger, 0 plus 1. So this is, so then what it means? It means 1 equals to A dagger 0. Okay? I just put the right-hand side to the left-hand side. Good. Okay, so you have 1, then what if I raise 1? What do I get? It becomes 2, right? So what is 2 then? 2 becomes, these are the eigenstate, n equal to 2, right? It becomes A dagger 1 divided by square root 2. right? I just put the square root 2 here. Is that okay? But then I continue to ask what is 1. We say 1 equals to a dagger 0 divided by square root 2, right? So this is equal to a dagger square 0, means apply it 2 times. So similarly, you get a dagger on 2, right? You see this is just square root 3, right? And similarly, you will get 3 equal to a dagger to the power 3, 0, divided by 2 times 3. Okay, so you keep doing this, eventually, you just prove by induction or whatever, or just trust it. If the nth state, right, the nth photon state is just a dagger to the power n, operate on 0, but divided by square root of n factorial. Okay, so that is how you can construct a higher state. Okay, I'm a little bit slow, but I think it's okay. I think we can do it. Okay, so I will stop here. Any questions? And sorry for my mistakes. Okay, when I put a dagger to 2 here, what is n? Yeah, what is the value of n in this equation? 2. So isn't that I put 2 plus 1, 2 plus 1 here? Are you talking about this one, n plus 1?
I'm just talking about the general equation.
Yeah, but if you base on this, okay, so we flip again, right? Because now this n becomes this n. So 3, yeah, so 3 factorial. Yeah, good catch, yeah. Yeah.
My question is like,
Slide 11. Mm-hmm. This one? Oh, this one is not from the top equation. This is because we have a dagger, right? But we remember that I copied from before. A dagger equals to a dagger minus a dagger a, which is equal to 1. That's why I substitute a dagger equal to 1 plus a dagger a. This is a dagger. Yeah, I replace by this. Good. Yeah, question?
So let's say if I have a quantum circuit, right, or one of these gates, can I put